Okay, so for part one here of homework 9-2, we'll pick up question 1 and get as far as we can. Right? The lowest pitch tone to resonate in a pipe of length L that is closed at one end and open at the other is 200 hertz. Right? Which of the following will not resonate? And there obviously is more than one correct answer for this. Obviously, as you can see, I've circled the answers there. The key understanding, and I'm sure most of us are comfortable with this, but if it's closed at one end and open at the other end, then it only resonates the odd harmonics, right? So since the fundamental frequency is 200, we can only hit odd multiples of that, right? So 400 does not resonate because it's an even multiple of 200, so that's why that one is a correct answer for one that will not resonate. 600 is okay because 3 times 200, so it is an odd number. 1000 is 5 times 200, so again okay because it's an odd harmonic. 1600 here, I should have circled this one as well, right? I actually missed this one. So 1600 here should have been circled as well because it's the 8th harmonic, which is not an odd harmonic, so my bad, this should have been circled too. And then 1100 is not even a multiple of 200, right? So it's not even an odd or an even harmonic, it's just neither of the above. So actually, my apologies, this should have been A, D, and E, right, as my correct answers. So A, D, and E. So we'll see how many of you actually watch the video and how many of you just look at the answer here, and that will tell me if you paid attention. But anyway, question 2. Two pure tones are sounded together. A particular beat frequency is heard. What happens to the beat frequency if the frequency of one of those tones increases? So the key relationship here is the beat frequency is the difference between the two. The problem is, since we don't know which frequency is increasing, we don't know what happens to the beat frequency. If the higher frequency were to increase, then the difference would become even bigger, right? If this were 100 and this were 90, and the 100 were to increase, then that difference would become even bigger. It would become more and more than 10, right? However, if the higher frequency was not the one to increase, if instead the lower frequency increased, right, then the difference would actually get smaller, right? So if the smaller frequency increased, the difference between the two would actually narrow, right? So the beat frequency, the difference between my two frequencies, depends on which frequency is going to increase and which one decreases, or which one doesn't increase, I should say. But in any case, I don't have enough information to know what's going to happen, right? I just don't have enough information based on what they gave me. Now, if they told me the higher beat frequency would increase, then I know for sure the beat frequency there would increase as well. But anyway, so make sure you're comfortable with something like question 2. Question 3, hopefully just a basic standard understanding, right? But anyway, option D is the correct one here. In a pipe that's open at one end and closed at the other, the displacement acts as the closed end, and the displacement node, acts as the closed end, and the displacement antinode acts as the open end. Right? So just know that the closed end acts as a node, and the open end acts as an antinode. And my guess is most of us were already right on with that one. Right, so rolling on to question 4. Question 4 gives us a standing wave here. They give us the frequency. The key is how many wavelengths is that? Well, that's 3/2 of the wavelength, right? So 3/2 of the wavelength equals the length of the pipe, which is 60 centimeters, which tells me then the wavelength equals 2/3 the length of the string, I should say, not pipe, right? But so my wavelength equals 2/3 of 60, so obviously 40 centimeters. And then once I know my frequency and my wavelength, finding my velocity is pretty easy. So it's just multiplying the two, which actually gives me 276, but based on the answers they give me, 280 is the best answer for them. So then rolling on with question 5 here, only odd harmonics in a column of air at an open end and closed end, right? So we are only getting the odd harmonics. Has a frequency of 448 hertz. The next higher frequency has the next higher harmonic has a frequency of 576. What is the fundamental frequency of the air? Because they're telling me that it's open at one end and closed at the other, again, I know only odd harmonics resonate. So the consecutive harmonics that resonate are actually then going to be off by 2 times the fundamental frequency. Right? If these are the harmonics that resonate, then it's a difference of 2 times the fundamental frequency. So I found the difference and then divided by 2. Right? So the reason it's not just the difference there, the reason it's not just 128, because we're not just looking at a fundamental frequency where all of the harmonics resonate. If this pipe was open at both ends, then it would be 128 for the fundamental frequency. But again, I'm finding the difference and then dividing that by 2, since I'm jumping by 2 harmonics from consecutive harmonic to harmonic. So then question 6, really the biggest understanding with question 6 is, once again, as you read through this, make sure you realize that the second overtone means it's the third harmonic, right? So that's where my diagram came from over here. The third harmonic would have 3 antinodes, so 3/2 the wavelength equals the length of the pipe, so then going from there. But anyway, so I've got my wavelength to work with if I need it. Then solving this the rest way, like I said, hopefully becomes pretty easy at this point. They give me enough information. They tell me how long it takes to go down and back, so I just simply take 2 times the length of the wire, right? And I'm taking 2 times the length of the wire because it has to go down and back in 0.78, or excuse me, 7.84 milliseconds, so 0.00784 seconds. So finding the velocity, I just use distance over time, and once I find the velocity and once I have the wavelength, easy enough to find the frequency. So a good calculation question to make sure you're comfortable with the basics, but I think as soon as you got this set up, hopefully you all agree that it's not too bad to then actually solve it. At this point in the game, question 7 here is probably too easy, right? They give us the length of the pipe, they give us the speed of sound in air, right? And then they ask us which frequencies, what's the fundamental resonant frequency of the air column if it's open at one end and closed at the other, and open at both ends. So again, just a key concept, right? I don't mean to rehash this again and again, but it is important we understand. If it's open at one end and closed at the other end, it's going to be 1/4 the wavelength equals the length of the pipe. So then my wavelength would be 2.56, and then solving for the frequency, easy enough. If it's open at just one, or excuse me, at both ends, then the longest wavelength would be 1/2 the wavelength equals the length of the pipe. So I cut the wavelength in half, which, as we saw before, doubles the frequency, right? So again, question 7, my guess is you guys wouldn't have any trouble with that, right? Question 8, also probably pretty easy. An air column here, open at one end, closed at the other, is being designed so the second lowest frequency. And so really the only understanding is we're working with 3/4 instead of 1/4, right? Realizing that second lowest resonant frequency is actually the third harmonic. It's the second one to resonate, right? So they give me the frequency that corresponds with that. I know the length of the pipe, so wavelength would be, 4/3 the length of the pipe, so I can plug that in and then just solve from there. But anyway, right, just calculating this, I think, is probably easy enough for most of us. So, and again, feel free to pause the video at any time if you need to, but I'm going to keep rolling along because I bet you guys don't need to wait on me. So anyway, question 9 here, right? Also a good question for kind of focusing on the difference between, right, constructive and destructive interference. So the sound from a single source can reach a point 0 by 2 different paths. One path is 20 meters long, the second path is 21 meters long. The sound destructively interferes at that point. What is the minimum frequency of the source if the speed of sound is 340? So the key is, what does that path difference tell me, right? So since the sound is destructively interfering at that point, right, I know that the path difference has to be causing destructive interference, and I know then that the path difference has to be setting them off by 1/2 of a wavelength, right? So I can find the path difference easy enough, right? 21 minus 20, so 1 meter. And again, the key understanding is that path difference, that lowercase delta, right, that symbol that I'm not very good at drawing. But anyway, the path difference has to be offset by 1/2 of a wavelength, right? And that would be the minimum wavelength, or the longest wavelength, the minimum frequency, I should say, at which this happens. So if the path difference is 1/2 the wavelength, then obviously 1 equals 1/2 the wavelength, so the wavelength would be 2 meters. And then once I know the speed of sound in air and 2 meters, it's easy enough to find my frequency of 170 hertz. So again, this is the first difference that would give me the lowest frequency. If I wanted to find a higher frequency, I could just say this is offset by 3/2, and then plug that in, solve for the frequency, the wavelength, and then use that to solve for the frequency, right? So I could find the other frequencies at which this would resonate as well, but they did specify just the fundamental, the minimum frequency. Question 10 is almost identical once we get it set up to what we just saw in question 9, right? So a little bit more geometry involved here because we're walking parallel to the speakers. So here's the initial setup. The two speakers are 5 meters apart. We're 12 meters away from the wall, but we're standing right in the middle. We're equidistant from the two speakers, so we're the same distance here as we are over here, which tells me obviously that would be an area of constructive interference, because if they're identical speakers, they're in-phase speakers that emit the same frequency, then those two sounds are going to be meeting up in phase at that location, right? So then the person moves 1 meter along parallel to the wall, right? So they've moved, starting at this point, they've moved like 1 meter this way, or 1 meter this way. It really doesn't matter too much. But they're still 12 meters away from the wall. Right, so they've moved away, and she experiences destructive interference for the first time. So now she's over here, and she hears destructive interference. Well, the key to all these problems, whether you're trying to use the equations we saw in class or just think it through, and I would encourage really for the most part just thinking it through, right? The key is the path difference. So I can find, just using a little bit of geometry, right, by using Pythagorean theorem a couple times, I can find the change in distance between this r, right, my measurement from the closer speaker to my new point, and the other r being the further speaker away, and my further distance here, right? So all I did was I did the Pythagorean theorem twice, 12.09 again representing the smaller distance, 12.5 representing the larger distance. So then my path difference, again delta equals the difference between those two, is 0.41 meters. So conceptually, all you have to realize is if we're hearing destructive interference, right, if she's not hearing a sound at that location, it's because the waves are offset by half of a wavelength. Right? Since they were originally in phase, the only way they destructively interfere is if they're offset by half of a wavelength. Right? So that tells me then that my wavelength needs to be twice the path difference. Right? So the path difference equals 1/2 the wavelength, and double it. And then once I know that, I just plug in my speed for sound, and then my wavelength that I just found to find my frequency. Right? So this last half of it is really identical to what we just did on question 9, but the first part is a little bit more trig, a little bit more geometry involved, but nothing too tricky, right? Nothing you guys can't handle. Question 11 here is a good example about the way that I can make the beat frequency the trickiest, and hopefully this wasn't too challenging here, but person hearing two sound waves simultaneously. One has a period of 1.5 milliseconds, excuse me. The other one has a period of 1.54 milliseconds. What is the period of the beat due to these two waves? So they're giving us the period, which obviously is a direct relationship, or an indirect relationship, I should say, right, to the frequency. We know the frequency is 1 over the period. So I can find the frequency of the original wave, the first wave, by just doing 1 over the period, which is about 666.67 hertz. I can find the frequency of the second wave, which again, just inverting the period, so about 649.35. And then the only concept I have to understand is the beat frequency is the difference between those two. Right, so the frequency of the beat would be simply the difference between those two, so 17.32. So if that's the frequency of the beat, well, invert it one more time, right? The period of the beat would be 1 over the frequency. So 1 over 17.32, so 0.0577 seconds, right? So 1 over 17.32, about 0.056 or 0.0577 seconds. So that's how long, that's the period for one of these beats, right? So it happens every 0.0577 seconds, or if you prefer, 57.7 milliseconds. But anyway, I think, again, question 11 is about the trickiest thing I can do with the beat, and I would imagine most of us handled it hopefully pretty well here. But anyway, continuing on to question 12, which will probably be the last example, so I'll finish up question 13 here in the final part of this homework video. But two strings of identical material have the same radius, stretched with the same tension, and so the significance of that first sentence is we know they have the same velocity. They each propagate at 420. The fundamental frequency on the longer string is 528. What is the beat frequency for the difference between the two again, right? So the fundamental frequency is when 1/2 the wavelength equals the length of the string. So the wavelength, the fundamental wavelength, would be 2 times L. And since I know then, obviously, right, I know my velocity, I know the frequency at which that's resonating, I can find the length of the string from setting up the velocity equals frequency times wavelength. Right, I've got my velocity, I've got my frequency, and I know that the wavelength would be 2L. So I could either just solve for wavelength here and then plug it in over here, or just solve for it all at once. But in any case, I find out that the longer string is 0.398 meters long. So since the shorter string is 8 millimeters shorter, so in other words 0.008 meters shorter, then I can find the length of the shorter string. And again, the significance here is they both have the same velocity. So once I find the length of the shorter string, I just plug my 2 back in there, and I find the fundamental frequency of that string as well. And then to find the frequency of the beat, I just simply find the difference between the two. Right? So all I did here was I found the difference between my 2, and that's what I did. Right? So anyway, hopefully not too bad to set up. You kind of have to go forward and then backwards on this one to find the difference between the frequencies. But again, my guess is if you take your time, most of us probably can do pretty well with a question like this. So anyway, I'll wrap up question 13 in part 2 of this video.